Why is MEG different from EEG? They're really measuring the same underlying activity, which is what we're showing here. Is there a laser pointer?
Oh, yeah, it's.
I do have one.
No,
I'm trying to decide which one it is. Or, oh, there's not one on here.
no, it is.
No.
Big one?
Oh, the big one. Okay, all right. So that's what I'm trying to show here. So there's this neural current in red here, and that generates magnetic fields, which are shown as green lines here, and then the extracellular current, which is what EEG essentially measures, is shown in these yellow lines. And what you see on the right side over here is that these yellow lines are a little bit distorted relative to the yellow lines on the left side. And this is really just to depict what EEG suffers from. And the problem is that it runs into this barrier, the skull. And so it essentially distorts the EEG signals. So what you do is you really lose some spatial information as the signal goes from inside the head to outside the head with EEG, whereas magnetic fields just aren't distorted the same way by the skull. And that is the primary difference between MEG and EEG. They're really measuring the same underlying activity. They also both have the same temporal resolution, which is on the order of milliseconds. We could collect data faster, but the brain really doesn't go any faster. And so if you collect data at a faster rate than 1 millisecond, you're just filling up your hard drive. You know, I mean, it's just extra information. So really that's where both MEG and EEG have topped out, is collecting data at about 1,000 hertz, and that's pretty much where people stop. There are a few things that look like there might be some interesting activity if you collect data at faster rates, but there's no reason to go beyond 10,000 hertz as far as we know. So this is just another topic to talk about with regards to the skull. This is an infant brain, so when you're an adult, then your skull is fused, so it's all bone. So this distortion problem becomes more complicated when you have parts of skull that are there and parts of skull that aren't there, right? Because now you have differential distortion across the brain. So the EEG problem actually becomes more problematic in kids rather than adults. Really, you know, you still have this problem with holes in the skull, you know, your eyes and things like that, but it doesn't affect large parts of your brain as an adult. But with infants and children, so the infants, these are the holes in the skull that you probably know about, called fontanelles. These seal about a year of age. There's one at the top of the head, one at the back of the head. But the sutures, the plates, actually don't fully fuse until between 8 and 10 years of age. So that means that we really still have these complications along the seams for quite a while through childhood. The other primary difference between MEG and EEG is that with EEG you have to get the sensors to have a good electrical connection with the scalp. And so there are various ways that you can do that. This is one of the easier ways. This one uses saline solution. You know, we all know that water is a good conductor. Of course, you have to make sure that there isn't water flowing between these sensors. Otherwise, you bridge sensors before measuring any actual brain activity. But these systems are very child-friendly because all you do is dunk this whole thing. It has sponges. You dunk it in a pot of saline solution, pull it out, put it on the head, and you get really good impedances that way, so you get good connection to the scalp. And if you don't have too much hair, which fortunately infants at least don't have a lot of hair, then you don't get this bridging problem between sensors. MEG instead of actually attaching the sensors to the head, the sensors are inside this big plastic helmet. So the advantage of that, obviously, is you don't have to attach every sensor that you want. So if you increase the number of sensors, it doesn't increase the amount of time that it takes to get the participant ready for data collection. So this is really still a huge advantage for NEG, even with those easier to apply EEG nets. The other advantage is that there are some individuals and some patient populations who have sensory sensitivities who are very uncomfortable with having something on their head, right? And this one, if you just can get them close to the sensors rather than actually having to attach EEG leads, is still an advantage. So this is just a picture of the sensors that are inside the MEG system that we have here. You can see that they're all around the head, and that gives us spatial information similar to what we get with MRI. And I'll talk about MEG in contrast to MRI in a little bit. One of the disadvantages of not having the sensors attached to the head is that the head can actually still move relative to the sensors. So this can be a problem if you have head movement while you're trying to collect data, because you're smearing the information relative to any one sensor, right? So one of the advantages of our current MEG system is that we actually track head position at every data point, and because we know precisely where the head is relative to so this is how we've figured out where the head is relative to the sensors forever. We just didn't previously collect head position throughout data collection. So that's kind of the more recent advancement. And because of that, then you can actually re-register the head to one default head position for that whole scan. And it allows you to really get rid of that spatial smearing that happens because of head movement during the scan. And this is just an example of one data set of an evoked response where prior to movement is the black line, and you can see that you have considerable signal gain if you really get rid of that head movement. So I just want to mention just briefly again the temporal resolution, because this is the contrast relative to fMRI, right? So with MEG and EEG, we collect data every millisecond, so this is just an example of what we can see with that temporal resolution. So this is just a very simple response to a median nerve stimulation. All of the lines here are different sensors, so the magnetic field measured at the different sensors, so that gives you spatial information. You can't see the spatial information in this plot, but what you can see very nicely is the timing. So time 0 is when you present the stimulus, and this is over here is essentially the baseline, right? What is the baseline brain activity? And anything above that baseline, we assume is related to responding to the stimulus that you're presented with. So you can see at 20 milliseconds, there is the first response that you get from this median nerve stimulation. And the activity peaks in different areas, right? You can't see where it's peaking in this plot, but you can see that it pretty much dies out by about 400 milliseconds. So with fMRI, if you're collecting data every couple of seconds, all of this information is collapsed into one slice, essentially, right? One TR. So that's what you can't get with fMRI. And then what we do with MEG is we do source localization, so you can see what the timing is for a particular source. So this is actually the timing profile for the primary somatosensory source, and there are other sources that are activated as well. So what I've shown you so far is evoked responses, so you present a stimulus and you look at the response. The other thing that we can look at, because what we really have is a time series that we're collecting from each sensor, is neural oscillation. So the neural oscillations that we're looking at with MEG and EEG, have fairly good direct connection to the physiology in the brain, right? So you can actually see that there are periods where neuronal spiking is gated, for example, and you can, if you look at the summed response, then you can get these neural oscillations because the gating of that neural spiking. So the other real difference between fMRI and MEG/EEG is that it's a more direct measure of brain activity. So this is just an example of time courses. So this is just a few channels. We have 306 channels that we're collecting data from simultaneously. But it's a time series. So obviously, you can do Fourier analyses, of the combined signal, and you can look at the different frequency bands. EEG has been around for a long time, right? So we know that there are different frequency bands that are relevant to behavior, right? So there's a lot of literature out there already. So we have these physiological frequency bands that have been divided out into different frequency bands because of this correlation with behavior. So delta, theta, gamma are some of the common ones, and those are what are depicted here. Alpha is one of the ones that we see in resting brain activity. So if you have your eyes open, then in general alpha 10 Hz oscillations in the occipital lobe are generally suppressed. If you close your eyes, then alpha gets much stronger. So this is just an example of that. So here you can see nice oscillations. I can just tell you that these happen to be at 10 Hz. You can see that in the time frequency plot here, where you have much stronger 10 Hz oscillations when the eyes are closed. So we know that there's some physiological responses that correspond to these neural oscillations. So I also like to show this little movie just to kind of underlie the difference. So this movie, if I get my cursor out of the way, you can actually see the time window here. So this started at about 100 milliseconds, and it ends at about 400 milliseconds. And you can see that there's changes in activity across that time. So this is stimulus and a word stimulus. So you're listening to words, and the auditory cortex is responding to those words. So again, with MEG, what we're looking at is the change in timing of this activity within a much finer temporal resolution.
Can you see these changes without any stimulus?
So the interesting thing is that the background brain activity is actually larger amplitude than most of these evoked responses. So we take the same approach as fMRI, where we present the stimulus multiple times, right? So this is the averaged evoked response. So we're averaging out the background brain activity, but the background brain activity has a lot of stuff going on as it is, right? And that's the previous plot that I had showed you, just to show you the time series. That's just background brain activity. So you can, and that's what the physiological frequency bands are really focused on, kind of the ongoing brain activity. So alpha, for example. But the other way that I like to kind of differentiate fMRI and MEG is just looking at spectral plots, right? So with fMRI, you look up to about 0.25 Hertz, and with MEG and EEG, we're primarily looking in the range of, this plot is showing 0 to 40. A lot of people are looking from 0 to 100 Hertz at this point, so there's now high gamma that people are looking at with respect to cognition. There's not a lot that people are looking at beyond 100 Hertz, but there are some interesting things, and I had done a study previously that was looking at some of that stuff as well. So just as a quick summary, this now is temporal scale along this axis, and this is spatial scale along this axis. So you can see that EEG and MEG are over to the left relative to fMRI, but not quite as far down on the spatial scale as fMRI. And PET is over here, so it's kind of out of the picture. Also because it's more invasive than these two approaches. And all of these three things are invasive approaches, right? So obviously it would be great to get to a smaller spatial scale, but you can't do that non-invasively. Yeah?
Recording time less than 1 TR. It's typically the recording time
Yeah.
is less than 1 TR, can be longer than TR.
Yeah, what about the TR? So, yeah, so we collect, yes,
yes,
no, that's correct. Now, of course, you can collect data as long as you want with MEG, EEG. I mean, it will take up a lot of data, take up a lot of space. But
less than 1 second. But after TR, I take at least 2 seconds, 3 seconds.
Yeah, that's right. Yeah. So yeah, so the primary point of this slide is to say that the temporal resolution of EEG and MEG is finer than for fMRI. Oops. So I'm going to argue this point a little bit with the slide with some recent results. So this is a study that just came out of the group in Canada. Run by Sylvain Baillet, and he's been involved with MEG research for a long time. They did a retinotopic study, so this is, so if you present visual stimuli in different parts of the visual field, then you can create a retinotopic map on the visual cortex. And so this top map is the results from MEG, and this bottom map are the results from fMRI. And their conclusion from this study is that depending on the folding of the cortex, so if the cortex is very folded, then MEG actually can differentiate sources that are a millimeter apart. And if the cortex isn't very folded, so in the flatter parts of cortex, then the resolution was 7 millimeters. So this is this latest result. And there are a couple of other studies that have come out recently that are also arguing that MEG resolution can be probably in this range. Really argues against the current understanding or assumptions that MEG has much poorer spatial resolution than fMRI. So that's always been kind of the argument for fMRI over MEG, and there are recent studies that are arguing that point. The other thing that I just wanted to point out, this was a simulation study that I'd done a number of years ago. So the simulated activity are the little yellow blobs here amongst the red. So the red is just the identified gray-white matter boundary. So we activated parts of cortex that should be realistic because the activation was really following the folds of cortex and things like that. And what we were looking at is if you activate sources close by in frontal cortex, because that's where MEG tends to suffer a little bit more in spatial resolution, what is the spatial resolution and what is the temporal resolution that we can capture if we create these simulations and then do our standard source localization. So we're creating the data into sensor space and then adding noise, realistic noise, so real background brain activity that is more difficult for these algorithms to resolve. What is the resolution? So this top line is the one that's relevant, the keep sources. So the resolution or the error in our source localization was about 0.5 centimeter for this particular study. But what I wanted to point out is the latency. So what these algorithms are able to do is very precisely identify the latency of the simulated activity. And what is hard to see, and I realize it's still hard to see, it's hard to see on my screen, but we actually have two sources here that are highly overlapping. So they're offset by just 10 milliseconds. So this is a fairly difficult separation for an inverse solution. And even with these highly overlapping sources, our resolution, temporal resolution, for recovering those peak latencies. In this particular study, our data was collected at 300 hertz, so we actually only had data every 3 milliseconds. So our error is below our resolution. So it was quite good on the temporal scale. So I want to give you just a couple of examples of how we've used this with our Eeg studies, and then kind of some other directions that people are taking Eeg analysis at this point. So this is just an early study that we had performed, really looking at very basic visual processing. So we've learned a lot about the visual system from primate studies, for example. So we know that there are different visual streams, and so the central stimuli, that stuff that appears in your central visual field, is processed through different visual streams than stimuli that are presented in the periphery. We know that these sources localize to different parts of the cortex, which can be shown here. So the peripheral stimuli localize more interiorly than the central stimuli. And what we were really looking at was looking at the ventral and dorsal visual stream. So the ventral visual stream really is more interested in the details of visual stimuli, and the dorsal visual stream is really interested more in the temporal properties of those visual stimuli. So you can imagine that really this is more focused on peripheral stimuli, and one of the hypotheses there's across both human and primate literature suggested that there can actually be different pathways for visual stimuli to get to your visual cortex, and that stimuli from the periphery have kind of access to a fast pathway in order for you to respond to threats in your periphery that you perhaps don't know are there. And so this really argues for timing differences between these conditions. I won't talk about the temporal components of the stimulus, but we actually had these circular sinusoids alternating at different rates, and you can see that. So this is just a static stimulus. This is alternating at 3 hertz, 8 hertz, and 14 hertz. So you can see that the brain responds in kind with the stimuli. In this particular study, what we found is that there's a difference in timing in the parietal lobe between the central and peripheral stimuli. The onset of the time in V1 was not the same, even though the peak was different between these. So this is the point of this is to show that with Eeg we can see fairly small timing differences that we wouldn't have access to with some other modalities such as fMRI. So this is relevant because it really does indicate that there's a different pathway for the dorsal visual stream, and it's consistent with greater myelination and larger diameter cells in the dorsal stream, which has been shown in previous studies. So some of the other work that we've done is really focused on schizophrenia. So I looked at both visual and auditory stimuli across a number of different populations, but my real interest is actually in looking at multisensory integration. But there is literature that suggests that there are visual deficits in patients with schizophrenia as well as auditory deficits, and I'm not going to go into the details of these studies. But what I was really interested in is, how do we put this information together? So multisensory stimuli, when you hear and see things, your brain actually integrates that information quite seamlessly. But it turns out that it's actually pretty sensitive to a lot of parameters, including timing. So partly we decide what should go together based on whether things are synchronous in time, right? So if you hear a bird call and see a bird, but they're not close enough in time, then you don't put them together. Except that we have this really interesting thing in the fact that the speed of sound is slower than the speed of light, and so our brain is actually a little bit flexible in this timing because if you hear a bird call, it actually often is quite a ways away, and we're able to still integrate that and decide that it goes together. But it turns out that our brain is actually quite sensitive to the timing of those stimuli to decide whether that information should go together or not. And you still get the most robust multisensory response, which means that it's a response that is greater than either unisensory response. So it's a response where, if you just add the response between audition and visual, a multisensory response and enhancement means that it's greater than some of those two, right? So you get the most enhancement when the stimuli are perfectly synchronous. If things are asynchronous by about 100 milliseconds, then any enhancement goes away. You just don't have that at all. So it tells us that our brain is actually a little bit flexible, but only to a degree, right? So you can think about the most obvious example that we have is thunder and lightning, right? So we put that together cognitively, right? It has nothing to do with our brain kind of automatically integrating those pieces of information. If you have a lightning strike that happens 2 miles away, it's seconds before you hear the thunder, right? You're like, oh, there must be lightning or something like that. If you hear thunder or you see lightning, you expect that there will be a thunder crash, but that is experience-based, right? So what we're talking about here is at a very physiological level. So I'm interested in multisensory processing. I think it's very relevant to MEG because of this sensitivity to timing. And I'm interested in it with patients with schizophrenia because we have this long-standing discontinuity hypothesis in schizophrenia. And obviously, auditory information comes in through auditory cortex, visual information comes in through visual cortex. They're not in the same part of the brain, right? So how does your brain actually put this information together, and how does it decide that it should enhance information in such a small time scale within 100 milliseconds, right? So the general hypothesis was that patients with schizophrenia would have an impairment in their multisensory integration because of disconnectivity as a kind of broad deficit in those patients. So this is just an example of the paradigm that we used. Again, we're looking at both central visual stimuli as well as peripheral visual stimuli. The previous study was talking about how peripheral visual stimuli can actually respond faster. The other thing that's relevant with peripheral versus central is that it does appear that the parietal lobe and dorsal stream in general in patients with schizophrenia is more affected than ventral stream. So there's some type of sensitivity that maybe clinical populations have, because this is not specific, this peripheral sensitivity is not specific to schizophrenia. It seems to be a more general finding. And then there were 2 auditory stimuli, and the whole point of this task was they just had to decide whether the stimulus was near or far. But then the auditory and visual information are presented either synchronously or asynchronously to look at that manipulation. So these are just behavioral results, but it underlines the findings that I'll talk about in a little bit. And so if you focus just on reaction time, so this is the patient with schizophrenia, this is the healthy controls, and the auditory response was slower than the visual response. But you can see that just in general, relative to all the other stimuli, there is a group difference between the visual response, so the patients here are slower than the healthy controls responding to the visual stimuli. This is the behavioral benefit that you also see from multisensory stimuli, so you can respond faster when you have two pieces of information than when you have one. But what's interesting is that even though the patients were slower for the visual and they're about the same for the auditory, so you really need to worry about that, but even though they were slower for both of the individual channels, is one way to view this, they were statistically equivalent to the healthy controls when they were presented with multisensory stimuli. So this was kind of our first surprising response, because this is opposite of what we had expected, where we expected that disconnectivity would further impair them, and we really expected that their multisensory response would be similar to their unisensory response. We found a similar, I'm going to skip over that, a similar enhancement. This is an EEG study that we did first with the EEG response. So now the multisensory response is this black line still, and the auditory and visual responses. So here you can see this difference between the auditory and visual for the patients, where you just don't see that difference between the auditory or visual relative to the multisensory for the healthy controls. So what this is really showing is some enhancement of the response by the patients with the multisensory stimuli that you don't see in the healthy controls. So we did had the same task in our much larger study with MEG, and really this is just a replication of the behavioral data, but what I want to get to is the MEG data. So now we again do source localization with our MEG data so that we can look at the timing for specific areas. This is looking at the timing for the primary visual response, and for peak 3, 4, and 5, there's this group difference between healthy controls and patients, where the patients are slower than the healthy controls, and this is not with the multisensory responses. This is just the visual response alone. What we also found is that latency of those peaks are related to behavior. Well, only related to behavior for the healthy controls, actually. So if you look at processing speed, for example, you see this group difference where the patients perform more poorly on processing speed, which means that they're generally just slower. And in healthy controls, there's this negative relationship between latency of this visual peak and their processing speed. So for the people, healthy controls who have faster V1 latency, so their visual system responds faster, then they perform fastest with this processing speed. So they have the better score. In the patients, this relationship is lost. And it's the same for this working memory measure, except this is with peak 5 now. So there's this association between latencies, and what I just wanted to point out is that we're not talking about a large variance in latencies. It's still fairly small difference in terms of the timing here, 60 milliseconds, in association with behavior. So now this is the MEG data, even though it looks similar to the behavioral data. This is now looking at that peak 3 latency for the visual alone response, so the auditory or the visual stimulus, peak 3 latency, and then the multisensory response. So how does the visual cortex respond when you both hear and see the stimulus? And what we found is with the visual alone, then they still have this delay. This is what I had shown previously. But with the multisensory stimuli, all of a sudden this fairly early peak in visual cortex, the latency is statistically equivalent to the controls. This is also consistent with multisensory facilitation. So this is behavioral facilitation. So there's a correlation between the amount of facilitation that you see behaviorally and their peak 3 latency. So if you have a slower visual latency, then you actually benefit more behaviorally from having the multisensory stimuli. So this was not consistent with the disconnectivity hypothesis of schizophrenia, but it is consistent with this high noise theory of schizophrenia. So if you think that in general the brain of patients with schizophrenia has a hard time perhaps disconnecting with whatever internal things are going on and responding to external stimuli, having 2 pieces of external stimuli may help them kind of bump out of the resting state or whatever it is that is kind of slowing down their responses. So having these 2 pieces of information is consistent with them really benefiting from having essentially more information coming in. So the other way that we can analyze MET data, obviously, is to do time series analysis or time frequency analysis, and we've done some of this as well. In this particular study, we were focusing specifically on gamma oscillations, which are really above 30 hertz at this point. We were focusing on 30 to 50 hertz. People are looking a lot at the range between 50 and 100 hertz at this point as well. So this is just a plot of the responses. Time 0 is still when the stimulus is presented, and this is really just the evoked response here that you saw parts of. And then what we were focusing on was the gamma responses, which are up here. So we found significant differences in gamma power between healthy controls and patients with schizophrenia in a few different conditions. And in addition, these were related to, again, some behavioral measures that we obtained with this particular study. So we've also, a lot of the work that I've been doing recently is focused on pediatric populations. So this is just a recent pilot study that we did based on one of my data sets, and this was looking at infant data. So really just looking at resting neural oscillations. Do you see differences in the brain in these infants? And the primary study here was focusing on prematurity, looking to see if you see differences in resting brain oscillations in healthy controls versus patients who were born prematurely. What we looked at specifically in this study was, and I have other things here that aren't directly relevant, but with infants you can't really tell them to sit still, right? I mean, you can tell them, but they won't necessarily comply. So what we have is we have a lot of other pieces of information that we collect during data collection so that we can identify periods of rest that seem to be valid. Because like I had shown you previously with alpha, the 10 hertz oscillations, if you close your eyes, then you have increased alpha oscillations. It's the same thing with the sensory motor cortex that it's called the mu rhythm, but it's still at 10 hertz in adults, and it's the same thing where if the sensory motor system is quiet, then you have increased mu rhythm oscillations, and if you're resting, if it's quiet, then you have increased mu rhythm oscillations, and if you're active, then it suppresses those. So you really need to be able to control. So with infants and with the video camera, you can tell whether they're sleeping or not, right? And you can see whether their eyes are open. So you can control that fairly easily, the alpha oscillations. The mu rhythm oscillations you really don't have any control over because infants squeeze all the time. They're doing lots of different things. So this really allowed us to identify kind of true periods of rest. And there are a couple of interesting directions that people are going right now. And one is, trying to understand maternal factors with respect to infants, and how that has an impact on brains, as well as, early life experiences, right? I mean, that's maternal isn't the only piece that goes into early life experiences, but there's a whole kind of new field that is called the developmental basis of health and disease, right? So, it's really saying that, cardiovascular health and a lot of other things are probably really based in either the prenatal or infancy period, which really indicates that perhaps we can see these factors at a very early age, right? And can we actually see differences? So in this particular study, we also collected maternal measures of PTSD, so post-traumatic stress disorder. So you can get a measure of PTSD severity. And so we did a correlation between MEG resting oscillations and PTSD severity. And for this theta oscillation, so these are 4 to 7 hertz, you see a relationship between PTSD severity and theta power. And it's in the direction that, so developmentally, the neural oscillations, kind of the balance between low frequency oscillations and high frequency oscillations changes with development. And this is really the underlying idea behind this, is that the low frequency oscillations are really considered the long range connections, right? So if you're familiar with these oscillations at all, really the high frequency oscillations, and part of this has to do with the fact that low frequency oscillations have more flexibility in time because, the peaks take more time. So it actually allows you, with low frequency oscillations, allows you to link up things across the brain within a particular cycle of an oscillation, whereas with high frequency oscillations, they oscillate too quickly that you don't have any ability to actually link things up across long distances, because it still takes time for the signal to get from one place to another. So high frequency oscillations are really related to kind of local processing. Low frequency oscillations are related to more long distance communication. So in development, you have more low frequency oscillations when you're establishing long range connections, and that balance changes as you age, so that you have more high frequency oscillations as you get older, when actually the more regional areas of the brain really start coming online, right? So frontal, a lot of parts of the brain are really that well developed at birth, right? So what this indicates is that if you have, what we have is that with higher PTSD severity, you have higher theta power. So this is really indicating that the individuals who have moms with higher PTSD are consistent with slower development, right? Because theta, you have a decrease in theta as the infant's age. And so if you continue to have high theta, then it may be an indication of kind of delayed development because of that. So I'm going to jump now to some of the work we've done in terms of linking MEG with other measures. So one of the studies that I did more recently was really putting MEG and DTI data together. This was using the Joint ICA toolbox. There's plenty of evidence that suggests that there are white matter deficits in patients with schizophrenia. And we also have plenty of evidence from MEG that there are differences. And so we used the Joint ICA approach, putting MEG in as one of the modalities and the DTI map in as the other modality. For For the MEG, we were just looking at regional analysis, so we didn't include like all 306 sensors or even at the source level, because there's a lot of data here already. So we transformed the MEG data into one long time vector, and so this is essentially doing time versus space. But we did find these associations that showed significant differences by group. And this is just one of the examples, which I still think is incredibly striking. So the MEG component was associated with, so the healthy controls are the solid lines here, and the patients are the dashed lines. And so you see this very striking difference in amplitude in the MEG component, and this was in visual cortex. And this difference in the MEG was associated with differences in FA, the superior longitudinal fasciculus. And so this is very consistent based on where this difference was found in the MEG and the areas of FA that are relevant. And in addition, this particular component was also associated with a number of the behavioral measures in a way that makes sense, such that increased amplitude is related to better processing speed, for example, which is consistent with what you see here. This is some of the stuff that John Houck has done. This was really combining fMRI with MEG and trying to compare REST fMRI with REST MEG and see if we get anything that's similar, right? So with MEG, obviously, we can do connectivity analysis the same way as with fMRI, it's just on a different time scale, right? And that's what this is looking at, is just looking at eyes open for these are just the standard FNC matrices, but with the MEG data. So you can see group differences between healthy controls and patients with schizophrenia. And this was a summary of the results, which was the primary takeaway message is that there are some similarities and there are some differences, which to those of us who do MEG is not surprising. I think that these two technologies are really accessing different parts of what's going on in the brain. But we do think it's important to be able to access probably both measures in order to get a more complete picture of what's going on. And I don't know, maybe that's what Sergey actually talked about, because that's what he's been working on a lot recently is, if you have a piece of missing data, you can't just ignore it, right? And that's the argument for doing both MEG and fMRI. So the last thing I wanted to talk about is this is a different way to analyze data. This isn't our work, but it was presented at the MEG North America conference in November, and thought it was kind of interesting because it's a different way of approaching it. Really, the standard approach for MEG analysis at this point, to differentiate it from EEG, which primarily has focused on sensor level analysis. MEG really, the standard approach is you get your MEG data, you do source localization, and you do something with it, right? So if you're doing evoked responses, then you can look at the timing differences that I showed. If you're doing time frequency analysis, then you look at that. This approach isn't actually doing source localization with the MEG. It's trying to combine the fMRI and the MEG data by looking at similarities between those two. So what they did is they looked at like the MEG data, for example, and say, okay, so what is the response to looking at a hand? And how similar is that response when you look at a pair, right? So let's organize all of our data according to how similar the responses look relative to whatever it is that you're looking at. And so you have this similarity matrix for all the stimuli that you're presented with. In this case, it was visual stimuli. And do the same thing with fMRI independently. And so you have a similarity matrix for all of the visual stimuli for fMRI, and then link these two based on their similarity matrices. And what they then ended up doing was mapping out the timing based on how these things linked up based on the similarity matrices. And so, yeah, I'm not sure that this is the answer in terms of like how you actually link fMRI and MEG data. It's very difficult. I mean, we still don't really have a good way to answer that question because you're effectively measuring different things. So maybe we shouldn't actually be putting these pieces of data together. Maybe we should just be looking at the results in parallel. But it's still interesting to try to do because I really want an answer about how the brain works rather than two independent answers. Yeah?
How about the relay between, because one is in the finer scale, and other is doing the size, like, what is refining, what is doing it exactly,
Yeah, it's, it's still complicated, right? Because, so what they essentially did here is ignore the spatial information for the MEG and really just looked at the temporal information. And then the similarity matrix gives you this timing based on the fMRI spatial information, right? So I'm not sure that it's, that the answer, that this is the answer because you're ignoring all the spatial information. You actually do have spatial information with MEG. So people have tried to do some sort of refinement of spatial localization with fMRI versus MEG, something like that. The challenge is how do you figure out what to weight and what not to weight? Because what those of us who've been doing this for quite a while at this point, what it looks like is that there are some things that you see that are the same in terms of actual sources that show up. And then there are some things that are different. And we don't know which ones are going to be different and which ones are going to be the same. Right? So that's the challenge. Yeah?
Yeah, the fundamental difference between MEG and fMRI. MEG is surface because it detects the surface out of brain. fMRI is the volume imaging, it's inside the brain. So they should be taken into consideration when you compare.
Well, no, I think that's true. Although, I mean, you are measuring activity that is coming from the volume, right? I mean, they are inherently different in terms of, and this is why MEG and EEG have the inverse problem that fMRI doesn't have. But it's also because fMRI is applying energy to the brain, and MEG and EEG are not, right? So that's a you're actually manipulating the brain, and MEG and EEG is just a passive measurement, right? So that's the other. I mean, that's why fMRI is a volume thing, and MEG is a surface measurement. Right? I mean, that's why. That's why.
So, so you showed John how this work maps. Can you quickly go back?
Sure.
I just have one question.
Radio on.
Yeah. So I just want to understand cases where in fMRI you have sources that are bilateral, in MEG that have not be one side, like the auditory cortex. Any comment on why that is?
Yeah, so this was run through ICA, and it turns out that in a lot of cases, the auditory cortices aren't really synchronous in MEG, right? So when you have higher temporal resolution, then you can actually parse that apart. Right? It's separated into two separate components. That's kind of an artifact of the ICA. Not necessarily, as long as you still get the two components, then it's not really an inherent difference, I would say. But there are still some, so this slide really is designed to show the similarities. But these aren't all the components that were identified in either fMRI or MEG. And there are other components where you don't see all the same things.
The other thing, I'm not sure if it's correct or not, because I remember I hear some of the epilepsy folks, they would prefer EEG instead of MEG because they think that the orientation for MEG is tangential, right?
Yeah.
And the other one in particular, which means that probably MEG is less sensitive if the source is inside of the cranium, right? Whereas EEG is probably more, maybe if both of them are surface scalp information, but it might be more sensitive if your source is inside of the cortical.
Yeah, and I glossed over that, but it is an important. So there's been a number of simulation studies done that really indicate that unless it's a very, very precise, source that's active, like that is truly just radial. So the problem is that like you end up with a patch of cortex infected, which means part of it might be truly radial, and the other part it has a tangential component to it, right? And so, but there are cases, and there's been a lot done. The primary use clinically for MEG is with epilepsy cases. So there's lots of data out there. There are cases where MEG can see an epileptic spike and EEG can't. And there are cases where EEG can see an epileptic spike and MEG can't. The optimal is to do MEG EEG. So you get everything.
So you can see, say, simultaneous recording.
You can do, and that's, currently most of my studies are actually simultaneous EEG and MEG, and part of that is for the translation argument, because the argument that comes back from people from NIH is that, well, MEG isn't very widely available, so how is this going to translate clinically? And so if you collect both MEG and EEG with the idea that MEG is kind of the more research piece of that, and you can look for maybe a less sensitive marker in EEG, then you can translate it, to the clinic more broadly.
Because I think I caught the previous slides, and there is like, for example, the one we just standard FMC, there was always one category which is subcortical. I was just saying, like, to MEG versus EEG, would that be more reliable, or which side is more reliable?
Well, it turns out that it's not really that super trivial to actually combine MEG and EEG either, right? And it's not the same problem as you have with fMRI versus MEG, because you at least have the same time scale. But the fact is that it's much harder to solve the inverse solution for MEG. You don't have a lot of the variables that actually need, and there isn't a good way to really decide what the best one is. But yeah, no, it's there are definitely things that MEG and EEG are less sensitive to because it's not a volume measurement. So things that are deeper are harder for us to see. Absolutely true. So we tend to stick with cortex rather than subcortex. Subcortex sources. Yeah.
For cortex, can we actually find the fMRI from MEG and EEG, for example, combined with HRF and all of others? It can be estimated fMRI completely, or
Well, so I don't think it's that simple because one of the other things that I didn't really focus on, but I have in previous talks, like what is actually generating the MEG signal, right? So we need to have, these are excitatory postsynaptic potentials that, as far as anyone can guess, is the generator of the currents that we're measuring with MEG and EEG. So one single excitatory postsynaptic potential is not strong enough to generate a magnetic field outside of the brain. You need 100,000 that are simultaneously synchronous, meaning, and the advantage of these postsynaptic potentials is that they actually last for maybe 10 milliseconds or so, which means you have some time for summation across different neurons. But what it means is that you need 100,000 neurons to be simultaneously active within that 10 millisecond time window in order to get a large enough signal to measure with EEG or MEG, right? So fMRI is just looking at blood flow. It really doesn't care if those things are synchronous, like we mean really synchronous, right?
But if
In a
it's
very-
really
so-
synchronized, shouldn't be, you have to measure like sub-millisecond, right? If you are really talking about really synchronized with neurons.
No, because we're just talking about getting a signal that is measurable. So you don't have to measure at the sub-millisecond scale in order to measure that. We just know that at some point things get synchronous enough so that you can see this. And so, we're getting this summed response across neuronal activity is what we're measuring. But what that means is that fMRI might be seeing stuff that isn't as synchronous, right? So there are some stuff that I would imagine you could predict from the MEG signal using a model of, what you would expect the blood flow to be based on that. And I bet there's also other stuff that you do not see that MEG doesn't see, and so you won't be able to predict with the fMRI signal that's there, right? Because it doesn't have that synchronicity constraint. So there's always advantages of also not having a temporal resolution. Right? I mean, there always are advantages both ways, right? I mean, I've sold you on primarily the advantage of having high temporal resolution, but there are always advantages for not having high temporal resolution as well.
The question is, MEG gonna take over EEG, or they're gonna want to take over?
Well, so the problem is, right now is that MEG is still expensive. So, there's new technology out there. So the optically pumped magnetometers, which do not require, so right now our machine requires liquid helium in order to work. So the squids themselves that detect these very small magnetic fields are expensive to build, and it's expensive to maintain the machine. This new technology, the optically pumped magnetometers, are relatively cheap to build and don't require any liquid helium to maintain, which means that you could probably, so the high density, you need to have high density EEG in order for it to be comparable with MEG, right, with a high number of sensors. High density EEG systems are 100K. I mean, you can get some for maybe 50K, but they're not, you can get really basic, simple systems for 10K, 10,000, right? So that's cheap. 100K is a little harder to get. The current estimates for this new MEG technology is it probably could get to 100K. But right now, the dynamic range for the optically pumped magnetometers is limited. Like it can't even cover 0 to 100 hertz with a sufficiently low noise floor, right? And so, you wouldn't even get what you currently get with the current MEG systems. You have to have much more limited kind of interest field of view. So, there are still some technical challenges with that technology, but it is actually quite promising. So if that technology can change, then there is the potential that MEG could maybe kind of overtake, but there is still this fact that, they're really still seeing mostly the same thing. The generators are the same, but they have different sensitivities. So maybe do a combined version.